All right, welcome. This is the Math 1010 Module 6.5 video for dividing radical expressions. So let's dive into it. We have seen already this. If I have the square root of some fraction, that can be rewritten as the square root of the numerator divided by the square root of the denominator, right? And that fits for the square root or any root. So if I have the nth root of a over b, I can rewrite that as the nth root of a divided by the nth root of b. So this is valid as long as b is not 0, otherwise none of this has any meaning, right? So if I have an expression, and again, we saw some of this before, so this may be a recap. But if I have something like, say, the square root of 25 over y squared, I can treat this as the square root of 25 divided by the square root of y squared. And that simplifies down to 5 over the absolute value of y, right? If I have something like, where did that one go? Yeah, they didn't do it. Oh, yeah, they did. In the book, they start omitting this absolute value, and they just start calling it 5 over y, and that's then only really kind of valid for positive y's, right? So they stop making the distinguishing remarks of having it the absolute value, even though that is still the case. But they do just kind of come in here and say, well, y has to be greater than 0, which is still not entirely true, right? Y could be less than 0. It couldn't be 0 itself because it's in the denominator, but it still could be less than 0. And if it is less than 0, then we have that absolute value. But they come along and they say, we make the assumption that y is greater than 0, right? It is an assumption, right? It's sometimes a terrible assumption, but in this book, they start making that assumption and say, well, let's just pretend y is greater than 0 so we don't have to write absolute values. Okay. So let's look at a few of those. Let's say we've got the square root of 16 x to the third over y to the fourth z to the fifth, right? Each one of these guys can be broken up. The square root of 16 x to the third in the numerator, the square root of y to the fourth, z to the fifth. And since we're under a square root, we're looking for pairs of factors that can pull out. But I can also treat this as just the square root of 16, the square root of x to the third. I can break up products under their own square roots as well. The square root of y to the fourth, right, and the square root of z to the fifth. It's not necessary. You can think of it this way without actually writing it. The square root of 16 is 4. The square root of x to the third, I have one pair of x's that can come out, but I have one left over. And then in the denominator, I've got 2 pairs of y's that can come out. So y squared, 2 pairs, each term comes y squared. I have 2 pairs of z's that can come out. That comes out as z squared, but then I've got that odd z left over. And we can leave it like that, and typically you would. Okay. Let's look at this. We have the fourth root of 18, 8 to the ninth, b to the 5th over 3b. Oh, I'm sorry. Let's back this train up just 1 second. Apologize. This was written as the 4th root up top over the 4th root in the denominator of 3b. Right? Now, this is an example of where we might want to go the opposite direction, because I can't do anything with that 4th root of 3b. I don't have 4 factors of 3 in the denominator. I don't have 4 factors of b in the denominator. I can't do anything with that. But if I rewrite this as the 4th root of the entire fraction, maybe I can simplify some stuff. So I would have 18 a to the 9th, b to the 5th, all over 3b. Right? And now you can simplify this because it's a fraction inside there. 18 and 3 are both divisible by 3. That leaves me with a 6 up top. B and b to the 5th, I can cancel out 5 up top and leaves me with 4. So in the end, I've simplified it a little bit, and this is now 6 a to the 9th, b to the 4th. And I don't have a fraction anymore. The denominator is 1, it's gone. So I can take out what I can here. I have 2 groups of a, right? 2 groups of 4 a's. So that comes out as a squared. I have 1 group of 4 b's, so that comes out as b. And then that 6 is just 2 times 3. I can't do anything with it, so I leave it in there with that odd a that didn't come out in the groups. And that's as simplified as that will get. Okay. So we have those, and then the last thing, it's a short section. The last thing that we have is rationalizing a denominator. So if I have something like, say, let's say I have 3 over the square root of 2, right? This square root of 2 is irrational. And irrational numbers are awful to deal with in denominators, right? For example, the square root of 2 is that ugly number. All right, that's not very beautiful. But if I were to actually try to perform this division, that gives me an infinitely long string of decimals to put to the left of the division bar. And if you remember long division, you want a whole number there. So what you do is you move your decimals over all the way until you get a whole number. And you can't do that here because you'll never get a whole number. And it makes this division, it makes long division impossible. You'd have to round this number at some point and then estimate it no matter what you tried to do, and it's going to introduce error. And so what we would do then is rationalize that denominator, and I do that by multiplying by, in this case, the square root of 2, because if I multiply the bottom by the square root of 2, and of course the top by the square root of 2, because again, I'm now multiplying this number by 1 because it's root 2 over root 2, so I'm not changing the value of the number. But if I multiply the tops, that gives me 3 root 2. But if I multiply the bottoms, that's the square root of 2 times the square root of 2, which is 2. And now my denominator is rational. And it makes the division, if you were to do long division here, it makes it not terrible. And even though we don't typically end up doing long division because we get sick of division and this turns out ugly no matter what we do, it is common to rationalize your denominator. And so we would do that here by multiplying it by the missing root of 2 in the denominator. It gives us a whole number 2. It's a rational number in the denominator, and we're good. You might see, however, a number like this. Let's say we have 3x over the cube root of, let's say, 4x, right? So now what I have is a cube root, right? The first one that we did here is a square root, so I needed 2 factors. I introduced that second factor of 2. I have a cube root, so I need 3 factors. That 4 is already 2 factors of 2. So when I multiply, I'm going to multiply it by the cube root of what's missing to make 3 factors. So I need that third factor of 2, but I also need 2 more factors of x, so that I have 1, 2, 3 factors of x that I can pull out of a cube root. And of course, if I multiply something, the denominator by the cube root of 2x squared, I then of course have to multiply the numerator by 2x squared, so that all in all, this is 1 I'm multiplying, and it doesn't change the value. So I multiply these, this becomes 3x times the cube root of 2x squared, and I can't simplify any of that. But in the denominator, now I have 4 times 2, which is 8, but the cube root of 8 is 2. And I have x times x squared under a cube root. That's the cube root of x cubed. That is x. And I can simplify because I have an x as a factor in the numerator and an x as a factor in the denominator. Simplify that, and my final answer is then 3 times the cube root of 2x squared over 2. And done. So again, that was a short one. That's it. I'm going to break these videos up by section or module, whatever section. So that's it for this one. Thanks. See you the next time.